Hey everyone, welcome back. Today we're going deep, 30 minutes deep, into the heart of the electrical world, the alternator. From the moment Michael Faraday discovered electromagnetic induction, the world changed. But how did we get from simple wire coils to the massive 1,000 megawatt machines that power our cities? It's all about one core principle, moving a magnetic field past a stationary conductor. Whether it's the small unit in your car or the giant rotors in a hydroelectric dam, the magnetic dance remains the same. Let's break down the history and the physics before we dive into the four main types. First up, the automotive alternator. It's a claw pole, or Lundell machine. Why claw? Look at these interlocking steel fingers on the rotor. Inside those claws is a single copper coil. When we send a small DC current through the carbon brushes and slip rings into that coil, it creates a magnetic field. Because of the shape of the claws, it creates alternating north and south poles. As the engine belt spins this rotor at thousands of RPM, these alternating poles sweep past the three-phase stator windings. This induces an AC current, which is then converted to DC by a bridge of diodes, the rectifier. Brushes are the weak point here. They create friction and wear down, but they allow for incredibly precise voltage regulation by the car's computer. Now, for industrial power, brushes are a liability. Imagine a hospital generator failing because a $5 carbon brush wore out. That's why we use brushless alternators. These are essentially three generators in one. 1. The stationary field creates a small current in the spinning exciter coil. 2. That AC current is turned into DC by a rotating rectifier, a set of diodes mounted directly on the spinning shaft. 3. That DC then feeds the main rotor. This means no physical contact, no sparks, and virtually zero maintenance for the electrical components. It's industrial gold for reliability in data centers and critical infrastructure. What if we remove the need for an exciter entirely? Enter the permanent magnet alternator, or PMA. Here we don't create a magnetic field with electricity. We use permanent magnets, typically neodymium. This makes PMAs incredibly efficient, especially at low speeds. This is why you'll see them in almost every wind turbine and small hydro setup. There's no excitation loss, meaning every bit of mechanical energy from the wind goes toward generating power. However, the downside is that the magnetic field is always on. You can't regulate the voltage by changing the rotor current, so you need heavy-duty external power electronics to handle the raw output. Finally, we reach the giants of the power grid. These are categorized by their rotor shape. Salient pole rotors have protruding magnets, sometimes dozens of them. They are designed for low-speed applications like hydroelectric dams, where the water turns the turbine at maybe 100 RPM. To get a 60 Hz frequency at that speed, you need a lot of poles. Smooth cylindrical rotors, on the other hand, are built for high speed. They are used in steam or gas turbines, spinning at 3,600 RPM. At those speeds, centrifugal force is so high that protruding poles would fly off. They must be smooth, forged from a single piece of high-strength steel, with the coils tucked into slots. In summary, automotive alternators are compact and regulated. Brushless units are the kings of industrial reliability. PMAs lead the charge in green energy efficiency. And the grid giants keep our world running through sheer scale. Understanding these magnetic dances is key to understanding how our modern world stays powered. If you want more engineering deep dives, let me know in the comments what we should tear down next. Don't forget to hit that like button and energize your subscription. See you in the next one.